just a quick overview of what we have done in this course and where it might fit into what you can do with these topics in the future. Okay, first place, this course is sort of an antidote to most courses. Now, antidote is too strong. It means that there's something seriously wrong with most courses. Actually, the design of most courses is okay, but they aren't always executed in the way that's most beneficial to gifted and talented students. So we want to give you sort of an antidote to some of the shortcomings of courses as they're usually taught. And I'm not throwing stones at the teachers. The courses have to be taught in such a way that they're accessible to most students, but in the process, the most capable or hardest working students often end up not being served as well as we might hope. So, in addition, there's a picture that really isn't part of the general curriculum that I'm convinced is potentially extremely beneficial for students who are going to go a little ways into mathematics. Let's say at least through a traditional 4-semester calculus sequence and maybe linear algebra, discrete mathematics, although we don't do too much with that. Okay, so the first cornerstone is basic elementary functions. Basic elementary functions include basically 3 kinds of functions, and we're going to concentrate on 2 of them. In the very last week of class, we'll touch on the trigonometric functions. They can be constructed rather easily, and once we understand what's going on with power and exponential functions, it's pretty easy to at least get an initial handle on the trigonometric functions. Okay, so we study power, exponential, and we study in this course. We concentrate on power and exponential functions and their inverses. Again, basic elementary functions of power, exponential, trigonometric functions, and their inverses. I should complete that word "and." Okay. And then also the sums, products, and composites of these functions. Okay, we generalize the elementary functions, and generally the sums, products, and composites of the elementary functions are generally regarded as elementary functions. So we'll see how to do things with power and exponential functions. We're not going to do much algebraic analysis on trigonometric functions, but we will probably in the last week learn to construct them, which is actually fairly simple. Okay, by construction. Okay, well, let's say that just talking about power and exponential functions, but much of what we're saying here can apply to trigonometric functions as well. These functions have geometric properties and they have algebraic properties. And the 2 are closely related, and really one of the things we want to do is be able to connect the geometric properties of the functions with their algebraic properties. And one of the things that happens in most courses is the geometric properties of the functions just get pushed off to the side, and we concentrate on the algebraic properties. The algebraic properties are extremely powerful, but they're often applied in a vacuum. Typically, a student will come out of a pre-calculus course. Good heavens. Geometric? I transposed 2 letters there. That's a little scary. I'm sorry. I got sidetracked. Most students will come out of a pre-calculus course where you study these functions with no idea that this is what it was all about. No overall picture and no understanding of geometric properties. And this is a little strange because people will come out of geometry courses, which of course in my opinion have serious shortcomings. But they come out of these courses with very little geometric understanding of these functions, and again, without any understanding of the classification. We want you to come out of this course understanding this classification and understanding geometric properties. You will see the algebraic properties. Hopefully the geometric properties will give you something to relate them to. Now we're going to do quite a bit with the algebraic properties and the relationships. But we get to the geometric definitions of graphs, compass and straight edge, construction of at least a selected set, and actually what constitutes a dense set of those functions. Okay, so there's one of the main things that we want to focus on. These things apply in the real world. Elementary functions can be used to analyze things that we've observed in class, the behavior of a pendulum, the behavior of water flowing from a hole in the side of a uniform cylinder, temperature, approach to room temperature. We've observed all these things and we've tried to relate the graphs. And then things like population growth, compound interest, diffusion, waves. I've got that in parentheses because we probably won't have time to do very much with it, but everything that we're doing can lead us to an understanding of certain central aspects of waves, the spread of ideas in a culture, okay, spread of ideas in a population, the spread of epidemics. Now, ideas aren't necessarily epidemics, although sometimes I'm tempted to wonder. Population cycles in an ecosystem. You might have a predator and prey, and their populations tend to be cyclic, and we can see a little bit about why. And then physics and engineering. Okay, all these things involve elementary functions. Sometimes they involve other kinds of functions, but almost all of undergraduate mathematics and applied mathematics, at least up to a certain point, is built on elementary functions: power, exponential, trigonometric functions, their inverses, and combinations. Then we have combinatorics in statistics. Okay, now we don't go very deeply into this, but we lay a foundation for future study and a perspective that will benefit anybody who's taking probability and statistics courses, which are practically universal among most of the fields people end up studying in universities and colleges. So we just start with the idea of what happens with coin flips and with normal curves. Now, by this time in the course, because I'm addressing this both to somebody who hasn't had the course and to somebody who is approaching their final exam in less than 24 hours, we should understand. Okay, we should understand this scheme: power and exponential functions, pendulum, water flow, temperature approach, how we could graph those things, test whether these things are power or exponential functions, and many of the algebraic and geometric properties. Okay, then with coin flips and normal curves, we get into the idea of, well, I'm not going to detail the definition of combinatorics or statistics, but we get into this. And we construct a normal curve based on the histograms we get from analyzing coin flips. We also learn how to inductively determine the number of possible outcomes for the flips of, let's say, 10 coins, if we know the information for 9 coins, that sort of thing. Normal curve, properties of the normal curve, and we'll explore further how this is applied. Okay, matrix algebra, which is based in this course just on the same Demented model, which, of course, if you're seeing this, you don't know what that really means. It means you got 1,000 people, let's say, a certain number are sane, a certain number are demented, and then every week a certain percent of the sane become demented, a certain percent of the demented become sane. Fairly simple model that can be modeled with a matrix. Bug diffusion, a bunch of bugs on trees, and every day, 10% of the bugs in each tree migrate to each of the neighbors. What happens to the overall population configuration? The idea of a transition matrix that can that can model either this or this, and the idea of population vectors. Okay, so you've seen all this. You haven't seen some of these. I've underlined the applications that we've seen, but you've done stuff that's going to make these applications very easy. Okay, and then the idea of difference equations. I'm not going to discuss that too much right now, but we'll see that in subsequent videos.